Hello world, my name is Nikita Black and I'm happy to welcome you back to my channel. At the very beginning of the series I mentioned that my ultimate goal was to dive into the fascinating world of GPU computing. More specifically, judging by the title of the series, I wanted to explore how mesh shaders work. I mentioned GPU computing because at their core, mesh shaders are essentially compute shaders. However, before jumping into the topic, I wanted to build a solid foundation. My goal was to make every part of the graphics pipeline completely transparent, so there will be no mystery about why we do certain things or where different Vulkan concepts come from. That's why instead of jumping straight into mesh shaders, I decided to build the entire Vulkan framework from scratch. As I mentioned before, the title of the series is a little clickbait. Looking back, it probably should have been called something like Introduction to Vulkan Programming. But it is what it is. Today's episode marks the end of this preparation phase. We will finally complete our rendering framework by adding a graphical user interface using the famous ImGui library. I chose ImGui because, although it is a fairly complex topic, it ties together many of the concepts we've learned so far and prepares us for the real work ahead. In this episode, we'll learn how to work with buffers, how to upload data from CPU to the GPU, and how ImGui works under the hood. Of course, we'll also fix plenty of bugs along the way, and I'm sure we'll be using RenderDoc more than once. So I promise it will be an interesting journey. I do have one warning though. This episode is going to be a long one. There is simply a lot of material to cover. So grab yourself a coffee just like I did, or better yet, grab two, and let's start programming. If you don't know, ImGui is a library for rendering graphical user interface. The IM stands for Immediate Mode, meaning that as a user of the library, you don't maintain the state of your UI yourself. You don't create UI elements upfront, store them somewhere, and subscribe to events. Instead, everything happens every frame at runtime. Rather than creating a button as an object, you simply issue a command to render a button for the current frame, and at the same time check whether it was clicked. It's easier to understand with an example. Let's open the official ImGui page and see how rendering works. Here's the button I mentioned. The button doesn't exist as an object. You don't store it anywhere, and it's not a member of your class. Instead, you simply call a function. Internally, the library maintains the necessary state, but for your perspective, it's just a series of function calls. For example, here we tell ImGui to render a piece of text. It will be placed in the current window at the next available position. Then, on the next line, we render a button. At the same time, we check whether this button was clicked. Of course, the button isn't actually drawn at this point, but we will talk about that later. If it was clicked, we handle the event immediately. There are of course many other widgets available. Text inputs field, float sliders, combo boxes, checkboxes, radio buttons, pretty much everything you would expect from UI library. It's a very powerful framework. Here you can see several examples of what can be built with this seemingly simple approach. So, is it actually good? How does it differ from a traditional retained mode UI? In my opinion, it's a brilliant idea. From a performance perspective, it's very efficient because your UI code follows the normal execution flow. You don't need to jump to separate event handlers then a button is clicked. Everything is processed in one place, which also tends to be more cache-friendly. So from a performance standpoint, this approach has some clear advantages over traditional UI frameworks. Of course, it also has some drawbacks. For example, creating complex layouts or sophisticated animations can be more challenging. It's definitely possible, but in those cases you need to manage the required state yourself. For example, to keep track of animation progress. Still, for most use cases, it's incredibly simple and pleasant to work with. Another thing I especially like about ImGui is how portable it is. This is possible because the library itself doesn't actually render anything. Its job is simply to generate a vertex buffer, an index buffer, and texture data. More precisely, it generates the pixel data for textures, not GPU textures themselves, but just arrays of color values. It is then up to the render backend to convert this data into API-specific objects. In our case, we are using Vulkan, so we'll translate the generated vertex and index buffer into Vulkan buffers, upload the texture data into Vulkan image, and render everything ourselves. And that's exactly what we'll be doing in this video. Now let's make a plan for today's episode. Let's see what we can start implementing immediately and what we still need to prepare first. At the moment, we only have a Vulkan image. In our code, we use the image2D class, which is just a small wrapper around Vulkan image. As you may remember, this image2D represents device local memory. We even debug Vulkan memory allocator earlier to see how this memory is allocated. The important thing about device local memory is that the CPU cannot access it directly. This means that if you want to upload data generated on the CPU, for example the font texture that ImGui produces, we can't use image2D class because there is simply no way for the CPU to write into that memory. We will face the same situation with buffers. We will have device local buffers that are visible only to the GPU. So the obvious question, if the CPU can't access device local memory, how do we upload data? The answer is that Vulkan provides another type of memory called host visible memory. This is essentially GPU memory that the CPU can also access. As you can imagine, it's much slower because the GPU has to fetch the data from system RAM over PCI Express or another hardware interconnect instead of reading it directly from its own VRAM. The performance difference can be significant. A good rule of thumb is the following. If the GPU will read the same data many times, it usually makes sense to store it in device local memory. If the data is read only once or only a few times, host visible memory is often the better choice. The ImGui vertex buffer is a perfect example. ImGui generates a new vertex buffer every frame, even if nothing on the screen changes. The geometry may be identical to the previous frame, but it is still regenerated and uploaded again. The GPU reads those vertices once to render the UI, presents the image, and then immediately discards them. In this case, using a host visible buffer directly is perfectly reasonable. Otherwise, if you want to use device local memory, we would first need to allocate a host visible staging buffer, recreate a command that copies the staging buffer into device local memory, submit that command to the GPU, and only then would the data become available for rendering. As you can see, that's a very long process. We could certainly do it for ImGui, but it would only make the code more complicated without providing any real benefit. On the other hand, consider another type of data such as the control points that define our T-pod patches. These are created only once and remain unchanged for the lifetime of the application. In that case, it makes perfect sense to upload the data to device local memory once and keep it there, allowing the GPU to access it as efficiently as possible. I mentioned that host visible memory is much slower than device local memory. But how much slower is it actually? We can measure it. I have CUDA installed on my machine together with CUDA samples, and one of those samples is called bandwidth test. I ran it, and here are the results. As you can see, copying the data from host to device reaches about 13 GB per second, while copying the data from device to device reaches about 360 GB per second. So device local memory is roughly 30 times faster. But is 13 GB per second enough for our case? Absolutely. Let's do a quick calculation. So we have approximately 13 GB per second of host-to-device bandwidth. Since we are targeting 60 FPS, we divide this number by 16. This tells us how many bytes we can upload every frame while maintaining 60 frames per second. The result is roughly 230 million bytes per second. Now let's look at the size of an ImGui vertex. Each vertex contains 2 floats for the position, 2 floats for the UV coordinates, and 1 uint32 for the color. That's 5 4-byte values, or 20 bytes per vertex. If we divide our 230 million bytes by 2 bytes per vertex, we get roughly 11 million vertices per frame. If you divide that number by 3 to estimate the number of triangles, that's almost 4 million triangles every frame. Now let's compare that to a 4K display. My monitor has 4K resolution, which is about 9 million pixels. That means that in theory, even if we render one tiny triangle for every 3 pixels on a 4K screen, we could still maintain 60 FPS based purely on the upload bandwidth. That's pretty incredible. Of course, we are nowhere near that. ImGui uses vastly fewer vertices than this. So for our application, using host visible memory directly is more than fast enough. It saves us the complexity of staging buffer while still providing excellent performance. The next step is to create classes similar to our image2D wrapper. This time, however, we'll create 2 buffer classes, one for device local buffers and another for host visible buffers. As usual, let's start by writing the code. After that, I'll explain how it works, and then we'll decide what to tackle next. Let's start with the buffer class. This class represents device local memory. It is very similar to image2D. There aren't many differences, and most of the code follows exactly the same pattern we used for images. The main difference is that instead of image_create_info, we now use buffer_create_info. Let's go through it step by step. First, I define the usage flags. These flags can be provided by the user of the class, but I also specify sensible defaults. In most cases, I expect this class to be used for storage buffers, which, by the way, are the only buffer type currently supported by our rendering pipeline. I also enable both the transfer destination and transfer source usage flags. This means that data can be copied both into and out of the buffer. In practice, the transfer destination flag is almost always necessary because that's how we upload CPU data to GPU memory. The only exception is then the buffer is never initialized from the CPU and is used exclusively by GPU operations, for example, as an intermediate buffer used internally by the pipeline. The transfer source flag is less commonly needed, but it allows us to copy data from this buffer to another buffer or image on the GPU. It's not something we'll use very often, but there is no harm in enabling it by default. These usage flags are then passed to buffer_create_info. Everything else is fairly straightforward. I don't specify any additional creation flags, I provide the buffer size, and since the usage flags has already been defined through the user flags, there is nothing else to configure here. The remaining fields relate to queue sharing. Since our application uses only a single queue and doesn't share resources between multiple queues, we can simply ignore them. Next comes the memory allocation. This is almost identical to image allocation. I request a dedicated allocation and set the memory usage to auto, allowing the Vulkan memory allocator to choose the most appropriate memory type. In this case, I will allocate device local memory. The remaining allocation parameter stays at their default values. Finally, I call create buffer. After that, the buffer is ready to use. We can copy data to it, copy data from it, and bind it to shaders. The class also provides a few simple getters. A getter for buffer handle and its size, and as well as a destroy function to release all allocated resources. The host visible buffer is almost identical. The main difference is that it provides a little more functionality. Let's start with its usage flags. Again, they can be customized by the user, but the defaults are transfer destination and transfer source. Notice that I don't include the storage buffer flag by default. That's because in most cases, this class serves as a staging buffer, a temporary buffer used to upload data from the CPU before copying it into a device local buffer. The staging buffer itself is never bound to the graphics pipeline. There are exceptions though. As I mentioned earlier, the ImGui vertex buffer is one of them. Since we want to use that buffer directly from the shader, we simply provide the storage buffer usage flag when creating it. The buffer creation process is almost identical to the device local buffer. The only important difference is in the allocation flags. Here I specify the host access sequential write and mapped flags. The first flag tells the allocator that we want CPU write access to the memory. The second requests that the allocation be mapped immediately, allowing us to write to it directly with functions like memcopy. Again, with the usage set to auto, the allocator takes care of selecting the appropriate host visible memory type. I also added copy to buffer and copy from buffer helper functions. These are just thin wrappers around the Vulkan memory allocator's memory copy functions. Here I'm using the relatively new std span and std byte types. They provide a convenient way to pass data into the buffer or receive data from it. Under the hood, the pointer to the underlying data is passed to the Vulkan memory allocator. One nice thing about this helper function is that the library automatically handles cache management for us. For example, if the allocated memory is host coherent, we don't need to flush anything manually. After submitting the command buffer, all the data written by the CPU is already visible to the GPU. If the memory is not host coherent, however, the CPU caches must be flushed explicitly so that the written data becomes visible to the GPU. Fortunately, we don't need to think about any of that because the Vulkan memory allocator takes care of it automatically. The same applies when copying data back from the buffer. To make the interface even more convenient, I also added templated overloads. This allows us to pass a std span of any trivially copyable type, and it will automatically be converted into std span of bytes internally. That's not really a Vulkan feature, it's just a nice example of modern C++. Finally, just like the device local buffer, this class provides getters for the buffer handle and its size, as well as a destroy function. And that's basically it for the buffer classes. Next, let's prepare a couple more helper functions. As you remember, for images we created a small wrapper around image barriers. Since we will need barriers for buffers as well, let's create similar helper functions for both our device local and host visible buffers. We will also add a function that actually uploads the data from the CPU to the GPU. The idea is simple. We will use a host visible staging buffer as the source and a device local buffer as the destination, and issue a copy command between the two. With these helpers in place, uploading data to the GPU memory will become much cleaner and easier to reuse throughout the project. Okay, here is another helper function for creating a barrier. It's almost identical to the image barrier we defined earlier, except this time we are working with buffer-specific structures instead. As a quick reminder, the source stage and destination stage describe the kind of work the GPU is performing. They define the execution dependency. For example, if you specify the source stage as the vertex shader and the destination stage as the fragment shader, you're telling the GPU that if the fragment shader wants to access this resource, it has to wait until all vertex shader operations involving that resource have finished. However, this only established an execution dependency. It doesn't guarantee that the memory is actually visible to the next stage. As you know, the GPU has multiple levels of cache, and that's where the access masks come in. They control memory availability and visibility by ensuring that writes are flushed and caches are invalidated when necessary. For example, suppose the vertex shader writes to a buffer, and later the fragment shader needs to read from it. In that case, we specify a write access mask for the source stage and a read access mask for the destination stage. This tells Vulkan that the fragment shader must wait not only for the vertex shader to finish executing, but also until all of its writes are made available and visible before any reads begin. That was a quick refresher. The source and destination queue family indices are ignored in our application because we're using only a single queue family. For images, we had to specify an image sub-resource range, which allowed us to apply barriers only to specific MIP levels or array layers. Buffers are much simpler. Here, we just provide the buffer itself along with the offset and size of the memory region that should be affected by the barrier. Finally, we fill out the dependency infrastructure and call pipeline barrier function just as we did for image barriers. The next function is much more interesting because this is where we actually start doing some real Vulkan work. We begin with a validation check. Here we simply verify that the destination buffer is large enough to hold all the data we want to upload. Next, we create a host visible buffer. This will act as a staging buffer, a bridge between the CPU and the GPU. As you remember, the constructor itself doesn't allocate anything. It simply creates the C++ object. The actual Vulkan buffer and memory are created when we call init. By default, the buffer is created with both transfer source and transfer destination usage flags, which is exactly what we need here. Once the staging buffer is allocated, we simply call copy-to-buffer function. Since this memory is accessible from the CPU, Vulkan memory allocator copies the data directly into it. The library also takes care of flushing the memory if necessary, so once we are ready to submit the copy command, the GPU is guaranteed to see the correct data. Originally, I added a barrier here, but after thinking about it, I realized it's completely unnecessary. This function is only called on freshly created buffers that we have never been used before, so there are no previous operations to synchronize with. In this case, we can safely remove the barrier altogether. Next, we define the region we want to copy. Vulkan allows us to specify different offsets for both the source and destination buffers. But in our case, we simply copy the entire contents. If in the future you need to copy only part of the buffer, you can easily extend this function. After that, we fill out a copy buffer infrastructure with the source buffer, destination buffer, and copy region, and then record the copy command. It's worth remembering that this command doesn't actually perform the copy. Like every other Vulkan command, it simply records our intentions into the command buffer. The actual work happens later, then the command buffer is submitted to the GPU. The barrier that comes after the copy is actually important. The function receives the destination stage and destination access masks as parameters, and this barrier ensures that once the copy has completed, the upload data becomes available and visible to whatever stage will consume the buffer next. Finally, we end the command buffer and submit it. We already wrote this helper function earlier. I simply moved it from the implementation folder into the utilities because we'll be using it in several places. I adjusted the graphics manager accordingly. One thing to notice is that this submission doesn't use any semaphores or fences. We simply submit the command buffer to the queue. However, I realized I forgot one important detail, waiting for the work to finish. The function is called init-buffer-sync, so the name itself suggests that it should block until the GPU completes the submitted work. In this case, that's perfectly fine because this function is intended only for initialization. We upload the data once, wait for the transfer to finish, and then continue. You definitely wouldn't want to do this every frame because waiting for the queue would stall the CPU and hard performance. So the fix is simple. After submitting the comment buffer, we just wait for the queue to become idle. Once that happens, we know the copy has finished, and we can safely destroy the staging buffer because it is no longer needed. And that's it. Our data has now been uploaded to device local memory. I think we finally have everything we need to start rendering our GUI. Of course, I may have forgotten something, and if that's the case, we will fill in the gaps as we go. But the next step is to actually start working with the ImGui library itself. The plan is pretty straightforward. First, we'll add ImGui as a dependency to the project. Then, we'll write some very simple UI code, just like in the example we saw earlier, maybe a few buttons and some text. Finally, we'll figure out how to retrieve the generated data from ImGui and upload it to the GPU so we can render it ourselves. So let's take it one step at a time. Write some code, see what happens, and discuss both the implementation and any problems we run into along the way. To add ImGui to the project, we'll once again use CMake's fetch content utility. However, there is one small complication. ImGui doesn't ship with its own CMake configuration. If you look at the repository on GitHub, you'll notice there isn't even a single CMake list.txt file. That's not really a problem, the library is perfectly usable without it. We were simply spoiled by the previous libraries, which already had well-defined CMake targets. In those cases, all we had to do was make them available through fetch content, and everything just worked. With ImGui, we need to define the CMake target ourselves. Here, I create a static library target and list all the source files that belong to the ImGui. One particularly interesting file is the ImGui impl GLFE backend. As you can imagine, there are many different operating systems and windowing systems. Since ImGui is cross-platform, it needs a way to receive mouse, keyboard, and controller input regardless of the platform. The core library itself doesn't know anything about GLFE, SDL, Win32, or any other windowing system. It simply exposes an interface for receiving input events. One option would be to intercept all the input events ourselves through GLFE and manually forward them to ImGui. Fortunately, the library already provides backend implementations for the most common windowing systems, including GLFE. So we will simply use the GLFA backend, initialize it with our window, and all the input handling will work automatically. The remaining source files are just a core implementation of the library and all of its widgets. Next, I expose the include directory so that any target linked against ImGui can find its headers. After that, come the compile definitions. The first one disables obsolete API functions, meaning that if you accidentally use an outdated ImGui function, we will get a compile error instead of a warning. I generally prefer that because it keeps the codebase up to date. The second definition is a bit more interesting. Here, I tell ImGui to use a custom configuration file. At the moment, this file is simply a copy of the default configuration that comes with ImGui. We won't modify it yet, but later we will make a few Vulkan-specific changes there. For now, I want to keep it identical to the original, so it's clear that nothing special is happening yet. Next, I configure the target to use C++23, just like the rest of the project. Finally, I link the required dependencies. In our case, that's GLFA and Vulkan. I mentioned earlier that ImGui itself is graphic API agnostic, and that's still true. The Vulkan dependency is only needed because we will eventually make a few Vulkan-specific changes in that custom configuration file. With that done, we can simply link our new ImGui target to the rest of the project, for example to Graphics Manager, and start writing the initialization code. So let's create a setup function and see what needs to be configured. In the setup ImGui function, we simply initialize the ImGui library. The first thing I do is call the version check macro. It's not strictly necessary, but it's a useful sanity check. For example, if you happen to have multiple ImGui versions installed on your machine, it's possible to accidentally compile against one version of the headers while linking against a different library. This check makes sure that the headers and the compiled library actually match. In our project, that's very unlikely because we fetch and build ImGui ourselves. But all the official examples do this, so I keep it here as well. Next, I create the ImGui context. This object stores all of ImGui's internal state and is required before using any other part of the library. After that, I configure a few library options. The first flag enables keyboard navigation, allowing us to move between widgets with the arrow keys, tab, and so on. The next option makes windows draggable only by their title bar. We probably won't have many movable windows in this project, but it's still a sensible default, so I'll leave it enabled. Then I disable both the ini file and the log file by setting their file names to null pointer. By default, ImGui stores Windows position, size, and other state between runs, and it also creates a log file. We don't need either of those, so I simply turn them off. The next setting is relatively new. I haven't used ImGui for quite a while, and the library has evolved quite a bit since then. One of the newer additions is lazy texture creation. In older version, ImGui created a single font texture during initialization, and the texture lived for the entire lifetime of the application. That's no longer the case. Now the library can create or recreate textures on demand. For example, if you add a new font at runtime or change the font size, ImGui automatically generates a new font atlas. This flag enables that behavior. Everything after that is purely cosmetic. These are just the colors used by the UI. I didn't come up with them myself, I borrowed the dark theme from Cherno's repository because I really like how it looks. The next step is loading a font. First, we need to make the font available to the application. I added the OpenSense regular font to our resources, and, just like we did with the shaders, I embedded directly into the executable using the CMRC library. That way, we don't need to load any external files at runtime. To do that, I create a resource library called FontSlip, link it to the application, and add the font as a resource. The process is exactly the same as with our shader resources. Now that the font is embedded into the executable, we can retrieve its data. First, I verify that the resource actually exists, just to catch any typos. Then I use the CMRC virtual file system to access the font data. Finally, I use the ImGui's font API to load the font. The first thing I configure is the glyph ranges. These ranges determine which characters should be included in the font atlas. I'm simply using the default ranges, which contains the basic Latin alphabet, digits, and common punctuation characters. After that, I call build ranges, and the next thing we need to decide is the font size. Here I'm using a base font size of 32 pixels. As you can imagine though, those 32 pixels won't look the same on every machine. For example, I'm running at a 4K resolution with a display scale factor of 2. If you're using the same 4K resolution but with a scale factor of 1, the font will appear much smaller. To compensate for that, I'm trying to determine the ratio between the physical frame buffer size and the logical window size. Since my desktop is scaled by a factor of 2, I multiply the base font size by that scale factor. The goal is that if I change the desktop scaling, the apparent font size remains roughly the same. This should at least make the UI look reasonably consistent across different machines instead of being either tiny or enormous. Unfortunately, DPI scaling is still a bit of a mess. I'm using Ubuntu 20 with X11 windowing system, and X11 handles scaling quite differently from other platforms. Windows uses a different approach, and I honestly don't know how this behaves under Wayland because I haven't tested it there yet. What I'm doing here is querying both the logical window size and the frame buffer size. On X11, those values are different, which lets me estimate the scaling factor. Whether this works correctly on other platforms, I can't really say. High DPI support is still surprisingly confusing, and even ImGui doesn't provide a single solution that works everywhere. It's mostly a matter of experimentation, so if you know a better cross-platform approach, let me know in the comments. Once we have the scaled font size, we call add font from memory to build the font atlas. Looking at this code again though, I think I spotted a bug. Here, I'm setting font data owned by Atlas to false, which tells ImGui that it does not own the font data and that I am responsible for keeping it alive. Internally, ImGui simply stores a pointer to that memory. The problem is that the font data comes from a local variable. As soon as this function returns, that memory is destroyed, so ImGui ends up holding a dangling pointer. That will almost certainly lead to a crash later. That's actually interesting because I've been using this code for quite some time, and I was convinced that ImGui copied the font data internally. I quickly checked the source code, and apparently it doesn't. So we need to fix that. The easy solution is to let ImGui own the font data. Here we allocate the memory ourselves and pass the pointer to the library, and let ImGui free it when it's no longer needed. Also here I'm using memcopy just because the CMRC file system returns as an object with a pointer to const data, while ImGui requires the data not to be const. We could of course use a const cast, but memcopy will also work fine. Next, we initialize the GLFW backend. This simply connects ImGui to our GLFW window so it can receive input events. With that, the basic ImGui setup is complete. I call this initialization directly from Graphics Manager init. At this point, it doesn't depend on the Vulkan device, so we can initialize it as soon as the Graphics Manager starts. During shutdown, we first shut down the GLFW backend and then destroy the ImGui context. Actually, looking at the code, I noticed another small mistake. This cleanup currently happens in destroy device function, but that's not the right place. It should be moved to the general destroy function instead. Let's fix that quickly. At the beginning of every frame, I call the backend's new frame function and then start a new ImGui frame. At the end of the frame, I call ImGui render. This is where ImGui generates all of its rendering data, the vertex buffer, index buffer, and any texture updates that are needed. Our job is simply to retrieve the data and upload it to the GPU. This step itself doesn't depend on Vulkan, so technically it could even run in parallel or slightly earlier in the frame. For simplicity though, I'm just calling it right before we begin the composition pass. Now, let's create a few dummy widgets and see what happens. As you can see, using ImGui is incredibly simple. Since we already did all the setup inside the Graphics Manager, creating the ImGui context and initializing the GLFW backend, all that's left to do here is describe the UI we want to render. The first thing I do is specify that the next window should appear at position 00. Then I call ImGui begin, which starts a new window. In ImGui, every begin should always have a matching end, and that's exactly what we do here. Inside the window, I add a text widget and then I create a button. Then the button is clicked, I simply print a message to the console. Now, if you compile and run the code, we obviously won't see anything yet. We are creating ImGui widgets, but everything still exists entirely on the CPU. We haven't uploaded any of the generated data to the GPU, so nothing can actually be rendered. What's interesting though is that the UI is already fully functional. If you roughly guess where the button should be on the screen and click there, you'll see that the message gets printed. That's pretty cool. It demonstrates how ImGui works internally. Everything happens in memory first. The library builds the entire UI, processes mount input, performs heat testing, and figures out which widgets were clicked, all on the CPU. Rendering is a completely separate step. Now let's start building our own ImGui renderer, one piece at a time. First, we will take a look at how ImGui organizes its rendering data and how we can retrieve it. After that, we'll start uploading it to the GPU. We'll begin with just vertex data. Once we get something on the screen, we'll move on to the more challenging part, handling textures. So let's start writing some code. We will render the user interface inside the draw ImGui function. Right now, the function contains several placeholders and to-dos, which we will gradually replace with real implementation as we build the renderer. The first step is to retrieve the draw data from ImGui. In our current example, this data contains the geometry for our window, text, and button. More generally, it represents all widgets that need to be rendered for the current frame. Next, I prepare the push constant data. As you may remember, the GPU processes vertices through several coordinate spaces. One of which is clip space. In Vulkan, clip space is a normalized cube where x and y coordinates range from -1 to +1, while the depth ranges from 0 to 1. Since we are rendering a 2D user interface, we don't care about the depth coordinate. What I'm doing here is constructing an orthographic projection matrix on the CPU. This matrix converts screen space coordinates into normalized device coordinates. For example, on my desktop I have a 4K monitor, so widgets' positions are specified in pixel coordinates, such as 200, 300. The GPU doesn't operate on those coordinates directly, it expects values in the normalized -1, +1 range. This projection matrix performs that conversion. We upload it as a push constant once per frame. Since the window can be resized, the display size may change, so we need to update the matrix every frame. After that, we iterate over the command list generated by ImGui. A frame can contain multiple command lists, although in our case there will most likely be only one because our interface is very simple. For each command list, we retrieve the vertex data and upload it into a GPU buffer. As we discussed earlier, we'll use a host visible buffer so the CPU can write the vertex data directly. ImGui also generates an index buffer for the geometry, so we need to upload the index data as well. One interesting detail is that ImGui uses 16-bit indices. This is probably one of the reasons why it can generate multiple command lists. If the total number of vertices exceeds the range of 16-bit indices, the geometry has to be split into separate lists. We'll store both the vertex and index data in a single buffer and use offsets to place each block of data at the correct location. Once both buffers are uploaded, we need to bind them so the shader knows where to read the data from. We'll implement this part a little later. Each command list also contains one or more draw commands. I haven't looked into the implementation details, but I suspect this is mainly related to clipping. For example, if part of the window extends outside its visible area, those widgets need to be clipped. ImGui likely creates separate draw commands for different clipping regions, which allows it to render complex user interface correctly. For each draw command, I first retrieve the display offset. In our application, we don't use any offset, so it's simply 0, 0. I also obtain the display scale. Since we don't apply any global UI scaling, this value is 1, 1. Next, I retrieve the frame buffer size. This is ImGui frame buffer size, not the Vulkan frame buffer or anything related to GLFW. Then I calculate the clipping rectangle for the current draw command. ImGui provides this rectangle automatically. I perform a quick sanity check to ensure that it has a non-zero size. If the rectangle is empty, there is nothing to draw, so we simply skip that command. Finally, I create a Vulkan scissor rectangle. In Vulkan, the scissor defines which portion of the frame buffer is allowed to receive pixels. It uses screen space coordinates. And together with the viewport, it determines the visible rendering region. While the viewport defines the overall rendering area, the scissor allows us to restrict rendering to a smaller portion of it. Any fragments generated outside the scissor rectangle are discarded by the GPU. At this point, we can compile and run the application to make sure everything still works and nothing crashes. The next step is to create the GPU buffers that will hold the ImGui vertex and index data. The first thing I do is create two host visible buffers. Why two? It's the same reason we have multiple per frame resources everywhere else in the render. Imagine that during one frame, we upload the vertex and index data into the buffer and submit the work to the GPU. As you know, we don't wait for the GPU to finish before starting the next frame. The CPU immediately begins recording commands for the following frame. If we were to write new data into the same buffer while the GPU was still reading from it, for example in the vertex shader, we would end up with undefined behavior. That's exactly why we allocate multiple buffers. Each frame gets its own buffer that won't be modified until the GPU has finished using it. As usual, these buffers are created during device initialization and destroyed, then the device is destroyed. When creating them, I specify that they will be used as storage buffers. I also give buffer a fixed size of 10 megabytes. Later in the code, I check whether the uploaded data fits into that limit. If it doesn't, the function reports an error. Of course, this is only for simplicity. In a real application, you would typically use dynamic allocation. For example, in another project, I use a smart buffer that automatically grows when more space is needed. Here, however, I keep the implementation intentionally simple so it's easier to follow. Next, I extend our frame data structure. Besides the command buffer and descriptor sets, it now also stores a pointer to the current ImGui buffer associated with this frame. Let's look at what changed inside draw ImGui. Since the function now receives the current frame data, it has access to everything it needs to update the push constant. Here, I'm using the current command buffer together with device and the pipeline layout to upload the orthographic projection data. Strictly speaking, it's not a full projection matrix anymore because the data is simplified, but the idea is the same. So I still refer to it as the orthographic matrix. Next, I introduce a variable that tracks the current offset inside the buffer. As we upload data, we want to append it, rather than override what is already there. Then, while iterating over the command lists, I create descriptor buffer info and update the descriptor set. This is very similar to what we did earlier than updating the image descriptor for the full-screen triangle. The difference is that this time we are working with buffers instead of images. After updating the descriptor set, I store the binding slot associated with this portion of the buffer. Remember that we are using a single large buffer containing all vertex data for all command lists and all index data. By updating the descriptor, we are telling the GPU that a particular range of memory contains the vertex data for the current draw call. The index data is handled differently. Unlike vertex data, index buffers are a dedicated concept in the graphics pipeline. They are not treated as ordinary storage buffers and have their own Vulkan binding command. The ImGui library gives us two things: a list of vertices and an index buffer that specifies which vertices form each triangle. The GPU then processes those indices internally. This allows it to perform optimizations such as vertex caching. If the same index appears multiple times, the GPU can often reuse the already computed vertex instead of running the vertex shader again. That's why index buffers are treated as a special resource. To bind the index buffer, I call Vulkan's bind index buffer command. Here I specify the buffer containing the index data, the byte offset where the index data begins, and the index type. As I mentioned earlier, ImGui uses 16-bit indices, so we specify the corresponding Vulkan index format. To summarize, the vertex data is accessed through a storage buffer descriptor because we fetch the vertices manually in the shader, while the index data is bound separately using Vulkan's dedicated index buffer mechanism. After binding the index buffer, I upload another push constant containing the descriptor binding slot for the vertex buffer. This isn't the first push constant for this draw call. We already uploaded the orthographic projection data earlier. Therefore, this second update starts at an offset immediately after the previous data, so let me append the new data value instead of overwriting the existing push constants. Finally, I set the scissor rectangle. You may notice that I'm not setting the viewport here. That's because the viewport is already configured in draw full-screen triangle. Since the entire frame is recorded into a single command buffer and submitted only once, the same viewport remains valid for all subsequent draw calls, including the ImGui rendering. When they start the next frame, all of this dynamic state is reset, so we need to set the viewport again. However, we don't repeat it here because the viewport remains exactly the same for the ImGui rendering as it does for the full-screen triangle. Finally, I issue the draw command. This time I'm using the indexed version, command draw indexed. Previously we used just draw. where we simply specified the number of vertices to render. Now that we have an index buffer, we need the index draw command instead. The first parameter is the number of indices to draw. That's why, when we bound the index buffer earlier, we only specified the buffer and the offset. We didn't specify its size. The number of indices to use is provided here during the draw call. The next parameter is the instance count. Since we are rendering only a single instance of the UI, we simply set it to 1. Then comes the first index. This specified the starting index within the index buffer for the current draw command. After that comes the vertex offset. This value is added to every index before the corresponding vertex is fetched. In other words, it shifts the base vertex for the current draw call. These two parameters are necessary because a single vertex buffer and a single index buffer can contain data for multiple draw commands. As you can see, we are iterating over the ImGui's draw commands. Each draw command needs to begin reading its indices and vertices from a different location within those shared buffers. The final parameter is the first instance. Since we are not using instancing, we simply set it to 0. At this point, the code compiles successfully. However, if you run the application, it obviously won't work, and I'm sure you already know why. That's right, we don't have any shaders for rendering ImGui, and we also haven't created a graphics pipeline for it yet. Let's try to run the application anyway. I already have the Vulkan configurator running, so the validation layers are enabled. As soon as I launch it, we immediately get an error. This error doesn't actually come from the Vulkan validation layers. It's reported directly by the Vulkan memory allocator library, and the message is quite clear. We are creating buffers using the second version of the buffer usage flags, but the allocator hasn't been configured to support them. The error tells us exactly what needs to be done. When creating the allocator, we have to enable the maintenance 5 feature by setting the corresponding allocation flag. So let's make that change and fix the problem. Now that we have fixed the allocator issue, we can run the application again. This time, the Vulkan validation layers report the actual rendering problems. At the moment, I see 2 different validation errors. The first one tells us that we issued a draw call without binding a graphics pipeline. That's expected, we haven't created the ImGui pipeline yet. The second error is related to our ImGui buffer. We were using the same buffer for both vertex and index data, but we created it with only the storage buffer usage flag. As you may remember, an index buffer is treated as a special resource in Vulkan, and it requires its own dedicated usage flags. So the first thing we'll do is add the index buffer usage flag when creating the buffer. The second step is to create a graphics pipeline for ImGui. This pipeline will almost be identical to the one we created earlier for the full screen triangle, so I'll explain only the parts that are different. Here I updated the ImGui buffers by adding the appropriate usage flag. I also create the ImGui graphics pipeline at this point. And as always, I added the corresponding cleanup code so the pipeline is destroyed when we destroy the Vulkan device. Now let's take a look at the pipeline creation. As I mentioned earlier, it's about 90% identical to the pipeline we created for the full screen triangle. The main difference is the shaders themselves. For now, I've left it to do there, because creating those shaders will be our next step. The other important change is the color blending state. This time, we need to enable alpha blending. ImGui renders many semi-transparent elements, such as text. Each character is rendered as a textured quad, and the pixels outside the glyphs must remain transparent. To achieve that, we need blending enabled so the transparent parts of the texture blend correctly with the background. Everything else in the pipeline remains exactly the same. We are actually quite lucky here because the two pipelines are so similar. As I mentioned, when we created the full-screen triangle pipeline, Vulkan allows us to use an existing pipeline as the basis for creating another one. Since these pipelines differ only slightly, we could reuse the first pipeline to speed up the creation of the second. However, pipeline creation isn't a performance bottleneck for us at the moment, so I decided to keep the implementation simple and leave that optimization as a small exercise for you. The only thing left now is the shaders. As before, we'll build them incrementally. We'll start with the simplest possible version, just enough to get something visible on the screen, and then gradually add more functionality as we need it. Here are our long-awaited shaders. Let's start with the vertex shader. The first thing we define is the push constant block. It contains the data needed to transform ImGui's coordinates into Vulkan's normalized device coordinates. Strictly speaking, this isn't a full orthographic projection matrix, we are simply applying a scale and a translation to the ImGui coordinate system. These are exactly the 4 values that we uploaded at the beginning of the draw ImGui function. The push constants also contain the descriptor index into our array of storage buffer descriptors. As you may remember, we assigned this value when we updated the descriptor set for the current vertex buffer. Next, I define the vertex structure. This structure is an exact copy of ImGui's own vertex form. If you look at the ImGui source code, we will see the same layout. 2 floating point values for the position, 2 floating point values for the texture coordinates, and 1 32-bit integer containing the pegged vertex color. That's exactly what we defined here. After that, I declare our descriptor array. As you remember, our descriptor set contains only storage buffers, all bound to binding 0. However, binding 0 is actually an array of descriptors, 100 descriptors in our case. Next, I define the outputs of the vertex shader. These are the interpolated texture coordinates and vertex color that will be passed to the fragment shader, along with GL position, which is the special GLSL output representing the final vertex position. Now we can read the vertex data from memory. First, we use the descriptor index to select the correct storage buffer. As before, we've wrapped the descriptor index with non-uniform function. This is required when using descriptor indexing. Technically, in this particular shader, it isn't strictly necessary because every invocation of the draw call uses the same descriptor index. Even if we remove non-uniform, the shader would still work correctly. Nevertheless, I always use it out of habit, so I don't accidentally forget it in situations where it is required. The selected descriptor points to a vertex buffer. From that buffer, we fetch the actual vertex using the vertex index. That vertex index comes directly from the index buffer. As you remember, ImGui provides us with the list of vertices together with the list of indices, describing how those vertices form triangles. Vulkan automatically uses the index buffer to provide the appropriate vertex index for each vertex shader invocation. Once we've loaded the vertex, we transform its position by applying the scale and translation from the push constants. Remember how these values are computed. The scale is actually 2 divided by the display size, where the display size is simply the size of the application window. This converts pixel coordinates into Vulkan's normalized coordinate system, so the final vertex position ends up in the -1, +1 range required by the graphics pipeline. Finally, we write the position to GL position. This is a 4-component vector. The third component is the Z coordinate, which we simply set to 0, because we are rendering a 2D interface and don't use depth. ImGui already provides its vertices in the correct drawing order. The ground elements are rendered first, while later triangles naturally overwrite earlier ones unless they are transparent. Since all geometry lies on the same plane, there is no need for depth testing, so every vertex uses the same Z value. The last component is W, which we set to 1. If this value were different, the GPU would automatically divide the X, Y, and Z coordinates by W during perspective division. Because W is 1, the coordinates remain unchanged. Next, I extract the UV coordinates and store them in a GLSL 2-component vector. Finally, I need to convert the packed 32-bit color value into a vector 4. ImGui stores the color as a single integer where each channel is encoded separately, so I extract the individual color channels and convert them into floating point values. However, these extracted channel values are still in the 0 to 155 range, while GLSL output colors I expect to be in the 0-1 range. In GLSL, a value of 1 represents the maximum intensity of a channel, while 0 means the channel is completely absent. For example, 111 represents white and 000 represents black. Therefore, after extracting the individual channels, I should divide each one by 255 to normalize them into the 0-1 range. Now let's look at the fragment shader. At the moment, it is extremely simple. We don't do any texture sampling yet, we simply write the color received from the vertex shader directly into the color attachment. The UV coordinates are currently unused, and the push constants are also not used here. However, when we created the pipeline layout, we specified that the push constant range is available for all shader stages, so I still declare the same push constant block here as in the vertex shader. With shaders ready, the next step is to add them to our build system. As you remember, our shaders are compiled directly into the executable. We already have the helper functionality for this, so all we need to do is add the new shader source paths to the build configuration. The shaders will then be compiled automatically and embedded into the binary. After that, when we create the graphics pipeline, the shader modules should be available and the pipeline creation should succeed. Now, let's build the project and run the application. When we start the application, we immediately get a segmentation fault. Let's investigate what is happening. I run this under the debugger, and here we can see that the crash occurs when we try to copy the vertex or index data into the host visible buffer. Let's inspect the values. The size tells us that we are trying to copy 47,200 bytes. That already looks suspicious. This is the point where we upload the vertex data. According to this information, only 2360 bytes should actually be available. The problem is in this line. Our vertex structure is 20 bytes, and here I incorrectly create a span containing 2360 vertices. However, 2360 is not the number of vertices, it is the total size in bytes. So we accidentally telling the program to copy 2360 times 20 bytes instead of just 2360 bytes. The fix is simple. Instead of passing the total byte size, we need to pass the number of elements. The same issue exists for the index buffer as well, so we need to apply the same corrections here. Hopefully that fixes the segmentation fault. Now let's build and run the application again. This time, instead of crashing, we get another set of validation errors. The validation layers report that we never set the viewport. Apparently, I was wrong when I said earlier that setting the viewport once would be enough for the entire frame. That's clearly not how Vulkan works. Dynamic state is associated with the currently bound pipeline, so whenever we bind a different pipeline, we also need to set any dynamic state that pipeline expects. In our case, that means we need to set the viewport again after binding the ImGui pipeline. Fortunately, the fix is straightforward. We'll use exactly the same viewport as we did for the full-screen triangle. The viewport simply covers the entire application window. Let's make that change quickly. Okay, let's run the application again. This time, we don't see any validation errors or warnings, which is great. However, we also don't see any user interface, which is definitely not what we want. Let's figure out what's happening. I already have RenderDoc running, so I will launch the application, capture a frame, and inspect it. If you look at the color path, we can see that the screen is cleared first. Then comes the first draw call, which renders the ImGui window and its title bar. The second draw call renders the text and the button. So far, everything looks correct. But then we notice the real problem. Immediately afterward, we render the full-screen triangle, which completely covers everything that was just drawn. In other words, the UI is actually being rendered correctly, we simply paint over it afterward. The solution is straightforward. We need to change the rendering order. First, we render the scene into the render target, then we draw the full-screen triangle to copy the render target to the swap chain image, and finally we render the ImGui interface on top of everything else. Ta-da! And there it is. It works. Although we can't render textures yet, so no text is visible because it comes from the font texture, the UI itself is already fully functional. We can resize the window, click the button, open and close the window. This confirms that everything is working correctly. There is one small issue left. Then I close the application. The validation layer reports that some device memory was not destroyed. This isn't memory that we allocated manually, it was allocated internally by the Vulkan memory allocator library. I simply forgot to destroy the allocator itself during cleanup. Let's fix that now. The next step is to make textures work. As I mentioned earlier, recent versions of ImGui have changed the way textures are handled. Instead of expecting the application to create a single font texture upfront, ImGui now generates requests whenever a texture needs to be created, updated, or destroyed. It's our responsibility to process these requests and keep the corresponding GPU resources in sync. To handle this, I'll extend the draw ImGui function so that it listens for these texture update requests and creates or destroys Vulkan textures as needed. As usual, I'll write the code first, and then we'll go through it step by step to see how everything works. Here's what I added to the draw ImGui function to support textures. First, after obtaining the ImGui draw data, we can access its textures field, which contains all the textures currently managed by ImGui. Each texture has a status indicating what needs to be done with it. For example, a texture may not yet exist in our Vulkan backend, in which case its status is "want create". Likewise, a texture may later need to be updated or destroyed. Let's start with the creation case. If at runtime ImGui decides that it needs a new texture, for example because the font atlas has changed, it creates an internal texture object with the status "want create". It's then our responsibility to create the corresponding Vulkan image. To do that, I create and initialize a new image to the object. I specify a format that we already know is guaranteed to be supported. Then I configure the image usage flags. Since this texture will be sampled by shaders, it must support sampled image usage. And because we want to upload its contents from the CPU, it also has to support transfer destination usage. Finally, I specify that this is a color image rather than a depth or stencil image and provide its dimensions. Of course, we also need to keep track of these images. For that, I added a new member called ImGui Images to the Graphics Manager class. During device destruction, I make sure to destroy any images that were created. At this point, there are still two to-dos. The first is uploading the image data. As you may remember, earlier we created a helper function for initializing buffers. We now need something similar for images. That will be our next step. The second task is setting the texture ID. So what exactly is this ID and why do we need it? As you already know, ImGui is cross-platform, cross-vendor and cross-API library. It supports Vulkan, OpenGL, DirectX and other graphics APIs. Unlike vertices or indices, textures are represented very differently by each API, so ImGui cannot store them in a universal format. Instead, whenever ImGui wants to reference a texture later, for example when rendering a widget, it identifies the texture through a texture ID. According to the ImGui documentation, this ID is a 64-bit value that the backend can use however it likes. Since it's a 64 bits wide, it's common to store a pointer in it using something like reinterpreted cast. However, if you look closely at the ImGui source code, you'll notice that this type def is actually wrapped into a set of macros. This gives us an opportunity to customize how texture IDs are represented. We can customize the texture ID type when we integrate ImGui into our project. As you may remember, when we added ImGui as a dependency, we configured it to use our own configuration file. At that point, the file was essentially empty. We just copied the default version without making any changes. Now it's time to put it to use. In this configuration file, we can overwrite the default texture ID type and replace it with one that's more appropriate for our Vulkan backend. Instead of using the generic 64-bit integer, we can define the texture ID as Vulkan-specific type. This integrates much more naturally with our render and allows ImGui to work directly with the resources we manage. Let's make that change now. Here how it works. In the ImGui configuration file, I redefined the texture ID type to be Vulkan image view. As a result, when we compile ImGui, every texture ID used by the library will actually be a Vulkan image view instead of the default generic type. Then, whenever we create a new texture, we first create the Vulkan image. After that, we obtain its image view and assign it as a texture ID. From that point on, ImGui can refer to the texture simply by storing this image view. Later, during rendering, each draw command provides us with its unique texture ID. I first perform a sanity check, because at this stage the texture ID must never be null. If a texture has been created successfully, it must already have a valid image view. If it doesn't, that's an unexpected error that we don't know how to recover from. Once we have the image view, we update our descriptor set so that it points to the correct texture. After that, the shader can sample the texture normally. The only remaining step is to upload the actual texture data to GPU memory. That's what we will implement next. The init helper function performs a task very similar to our buffer initialization helper, which we didn't use by the way, but we just created this as an exercise. However, notice that its name doesn't include the sync suffix. That means that this function is intended to be used at runtime, when we already have an active command buffer and don't want to block until the initialization is complete. That's exactly our use case. We are creating images while the application is running, so we want everything to happen without stalling the rendering loop. A synchronous implementation would be much more complicated. We would have to allocate a separate command buffer, record the copy commands into it, submit it to the queue, wait for the queue to finish, and only then continue rendering the current frame. Instead, we'll upload the data as part of the existing command buffer and rely on proper synchronization through pipeline barriers, as you will see in a moment. The first thing I do is verify that the data we are uploading actually fits into the destination image. Next, I create a temporary staging buffer and copy the image data into it. This is necessary because our images are located in device local memory, which the CPU cannot access directly. As you may remember, the staging buffer serves as an intermediate step between CPU memory and GPU memory. Notice that this intermediate resource is still a buffer, not an image. Vulkan doesn't provide an equivalent concept of host visible image for this kind of upload. Then I define the image subresource that will receive the data. Since we are using a simple 2D image with no MIP levels and no array levels, the setup is straightforward. After that, I specify the image offset. We want to update the entire image, so the offset is 0. Then I provide the image extent, which simply describes the size of the image. Next comes the description of the source data in the staging buffer. We copy the entire buffer, starting at offset 0, because we created a dedicated staging buffer specifically for this upload. The next two fields, buffer row length and buffer image height, are only needed when the image data occupies a subregion of a larger buffer. For example, if you have a larger texture stored in memory, but only want to upload a small rectangular portion of it, these parameters describe that layout. In our case, the image data is tightly packed, so we simply leave both values as 0. Now we create the copy buffer to image info structure. Here, they specify the source buffer, the destination image, and the layout the destination image must be in during the copy operation. Before we can perform the copy, we need to make sure the image is in the correct state. That's where the first image barrier comes in. This barrier transitions the image from the source stage and source access provided by the caller to the transfer stage, because the copy operation executes in the transfer pipeline stage. The destination access mask is transfer write, since we are writing into the image. We also transition the image into the transfer destination optimal layout. For the old layout, we simply use undefined. Since we're about to overwrite the entire image anyway, we don't care about its previous contents. This allows the implementation to choose the most efficient transition, potentially discarding the old memory altogether. With the image in the correct layout, we can finally record the buffer to image copy command. After the copy completes, we insert another image barrier. This one transitions the image from the transfer stage to whatever stage we'll use it next. In our case, the destination stage is the fragment shader, the destination access is shader sampling, and the final layout becomes shader read-only optimal, which is exactly what the shader expects. I call this helper immediately after creating the image. Since the image has been just created, its source stage and source access are both none, because no previous operations have touched it yet. Then I specify the desired destination stage, destination access, and final layout. Finally, I need to destroy the temporary staging buffer, otherwise the validation layers would complain about leaked resources when the application exits. Now let's build a project and see if everything works. Unfortunately, it doesn't work. However, this error is actually quite interesting. The validation layer tells us that we are trying to execute a pipeline barrier inside a render path instance. And indeed, if you look at our graphics manager, we can see that we currently initialize ImGui textures during the compose render path. This is not allowed in Vulkan. If you look at the Vulkan specification, we can find the corresponding rule. There are actually quite a lot of restrictions around pipeline barrier, because synchronization commands have very specific requirements depending on where they are used. The relevant rule says that if the pipeline barrier is called inside the render path instance, then the old layout and new layout fields of every image memory barrier must be identical. In our case, they are different. During texture initialization, we transition the image from transfer destination optimal to shader read only optimal. This layout transition is exactly what Vulkan forbids inside the render path. So we have two possible solutions. The first option is to do what I mentioned earlier. Create a dedicated command buffer, perform the image upload there, submit it separately, and wait for it to complete. This would make the initialization fully independent from the render path. The second option is simpler. Move the texture initialization code outside of the render path. Since the problem is caused only by the location where they execute the barrier, we can keep the same asynchronous approach, but perform the image upload before starting rendering. Let's try this second approach. Let's try running the application after these changes. Unfortunately, we still have some errors. As usual, let's go through them one by one, starting from the first one. The first error tells us that we are using the wrong destination image layout in our copy command. And indeed, that's correct. This field should describe the layout that the image is expected to have during the copy operation. Since we are copying data into the image, the required layout is Layout Transfer Destination Optimal. This one is easy to fix. The next error is a little more subtle. After the initialization function finishes, I immediately destroy the staging buffer. At first glance, this might look reasonable because we no longer need it. However, this is incorrect because Vulkan commands are not executed immediately. When we call copy buffer to image, we are not performing the copy. We are only recording a command into the command buffer saying, then the GPU executes this command buffer later, copy data from this buffer to this image. So what happens in our code? First, we record the copy command that references to the staging buffer. Then, we destroy the staging buffer. Later, then the GPU finally executes the command buffer, it tries to read from the staging buffer, but the resource no longer exists. This results in invalid behavior. There are two possible solutions. The first option is to keep the staging buffer alive. We could store it somewhere and destroy it later, for example after a couple of frames. Since we use multiple frames in flight, waiting 2 frames guarantees that the GPU has already finished processing the command buffer associated with this frame. The second option is the one I'll use here. We can make this function synchronous. That means that we create a dedicated command buffer, record the copy operation, submit it immediately, and wait until the GPU finishes executing it. After that, we are safe to destroy the staging buffer because we know the copy has already completed. The downside is that it introduces a pipeline bubble. While the GPU is performing this copy operation, it cannot continue with other rendering work that depends on this synchronization point. However, in our case, this is completely acceptable. Texture creation will not happen every frame. In practice, we will update textures only once or maybe a few times during the lifetime of the application, so the performance impact is negligible. Let's change the implementation to use the synchronous approach. We are very close, but after running the application again, we still get another set of errors. Fortunately, this one should be much easier to fix. The problem is related to the submit function. During the initialization, I call the submit function without providing any semaphores, so both semaphore handles are null pointer. However, inside the submit implementation, I currently create semaphore submit information structures unconditionally, as if these semaphores always exist. This is incorrect, because Vulkan expects these structures to be omitted entirely, then no semaphore is provided. The fix is simple. Before creating the semaphore submit information structures, we need to check whether the corresponding semaphore handle is valid. If the provided semaphore is null pointer, we should not add the corresponding semaphore information to the submit operation. Let's add this check now. Finally everything works. However, we still don't see any textures on the screen. The reason is simple: we haven't updated our fragment shader yet. The rendering pipeline is already capable of providing the texture data, but the shader is still ignoring it. So the next step is to modify the fragment shader to actually sample and use the texture. Let's do that now. The shader changes are quite straightforward. The only thing we need to add is the missing push constant containing the descriptor index for our texture array. As you remember, this descriptor set is bound to set number 1. The descriptor set at slot 1 contains only an array of textures combined with samplers, which is why you don't see a separate sampler binding here. If we were using separate textures and samplers, we would need another binding or possibly even another descriptor set. Inside the fragment shader, we take the existing vertex color that was passed from the vertex shader and multiply it by the color sampled from the texture. The texture sampling function simply retrieves the corresponding pixel value from the texture. This is the way ImGui combines vertex color with texture data. Now, if we run the application, we finally see the result we were aiming for, which is pretty exciting. However, we are not finished yet. There are still some issues that we need to solve. For example, we can perform a small stress test by enabling the ImGui demo window. This is a built-in example window that demonstrates almost all functionality provided by the library. The good news is that we can now see the UI on the screen. We can interact with different sections and explore various widgets. However, if you open some of the sections, you may notice strange empty spaces where some characters should appear. This is probably because we currently only create the texture but do not handle texture updates. My assumption is that when we initially create the font texture, the atlas contains only the characters required by the currently visible UI. When we open additional sections, ImGui may require new characters that were not included in the original font atlas. Since we don't update the texture, those glyphs are missing, which results in empty spaces. So we need to implement texture updates and also handle the case when ImGui asks to destroy a texture. But there is another problem as well. The colors look washed out. As you can see, everything appears slightly gray, while it should have much more saturated colors. This is another interesting issue that we need to investigate. Here is what we have added. When ImGui notifies us that the texture needs to be updated, we do almost exactly the same thing we did during texture creation. The only difference is that during initialization we create a new texture, whereas during an update we simply reuse the existing texture and override its contents with new data. When ImGui requests that the texture to be destroyed, we locate the corresponding texture in our list of ImGui images, remove it from the container, and destroy the underlying Vulkan image. One interesting detail here is the blocking queue-wait idle call. This is necessary for the same reason as before. We must not destroy a resource that the GPU might still be using. Yes, this introduced a pipeline bubble, but in this case that's perfectly acceptable because texture destruction happens extremely rarely. In fact, I don't expect this branch of the code to execute very often at all. Even if it turns only 3 to 5 times during the entire lifetime of the application, the performance impact is completely negligible. Now, if you compile and run the application again, we can see that the missing glyphs are gone. The font atlas is updated correctly and all characters are rendered as expected. However, while experimenting with the demo, I noticed another issue. For example, if I open this menu, the rendering becomes completely corrupted. Looking at the validation layer output, we immediately get a clue about what's happening. The validation layer reports that when we update a storage buffer descriptor, the buffer offset must satisfy a specific alignment requirement. At the moment, we don't enforce this at all. We simply write data into our buffer at arbitrary byte offsets and then update the descriptor to point to the beginning of the data, without considering the required alignment. In my case, the validation layer reports that the minimum storage buffer offset alignment is 16 bytes. Of course, this value is hardware dependent, so it must always be queried from the physical device at runtime rather than hard-coded. This is actually a critical issue, and as you just saw, violating this requirement completely breaks rendering. So let's fix it right away. Now, with this fix applied, let's launch the application again. I open the same menu, and this time there are no more validation layer warnings anymore. That's good. Unfortunately, the rendering is still broken. I have mentioned this several times already, but this is probably the most frustrating part of graphics programming. Everything appears to be correct. There are no validation errors. The application renders something, and under certain conditions it even looks fine. But then, in other situations, it suddenly produces complete garbage. There are so many moving parts and so many subtle details that it's often very difficult to determine what actually went wrong. I spent quite a bit of time investigating this issue, and once again, RenderDoc was an enormous help. The bug turned out to be quite interesting. The problem is related to how I'm updating push constants. I keep track of the current push constant offset because every time I upload another piece of data, I want to append it after the previous one rather than overwrite it. That logic works fine as long as there is only a single push constant update. However, ImGui generates multiple command lists, and each command list can contain multiple draw commands. As a result, every time I issue another push constant call, I continue to increment the offset. For example, when I push the descriptor index for the texture, I expect it to be written at byte offset 20. The total size of the push constant block is 24 byte. The first 20 bytes are occupied by the scale, translation, and vertex buffer descriptor index, while the final 4 bytes store the texture descriptor index. That layout is fixed because the shader expects the texture descriptor at exactly that offset. Instead, my code keeps increasing the offset with every push constant update. So, although the fragment shader always reads the texture descriptor from byte offset 20, I'm writing it somewhere else entirely. As a result, the shader reads garbage. Even worse, I end up overwriting the data for the vertex descriptor, which means the vertex shader starts fetching vertices from the wrong buffer locations. That's exactly why the rendered geometry becomes corrupted. As I said, it took me quite a while to figure out because everything else looked perfectly valid. We allocated enough push constant space, we never exceeded its size, and there were no validation errors. The problem wasn't that we wrote too much data, it was simply that we wrote it to the wrong offset. The fixes, fortunately, were simple. Instead of maintaining a random push constant offset, I'll remove that logic entirely and use the fixed offsets defined by the push constant layout. That guarantees that every piece of data is always written exactly the shaders expect to find it. Now everything seems to work correctly. Or is it? If you look closely, you can still spot a few strange rendering artifacts. For example, this line doesn't look quite right. If I open some additional widgets, you'll notice that these checkboxes are rendered incorrectly as well. The underline beneath the hyperlink looks wrong, and some of these thin lines are clearly missing or distorted. Even more interesting, if I resize the window, these artifacts move around in unexpected ways. At this point, it's very difficult to tell what is actually wrong. As you can see, the validation layers don't report any errors. Most of the UI renders perfectly, and only a handful of small details are incorrect. Fortunately, the solution turned out to be surprisingly simple. I made an educated guess, and this time it happened to be the correct one. The problem was in the pipeline creation, more specifically in the rasterization state. When creating the pipeline, I enabled backface culling. It turns out that some of ImGui's geometry, for example certain lines and checkbox elements, uses the opposite Windig order. As a result, those triangles are incorrectly treated as backfaces and get culled. The fix is simply to disable face culling for the ImGui pipeline altogether. As you can see, everything now renders exactly as it should. We can explore the demo window, interact with all the different widgets, and get a good impression of just how much functionality ImGui provides. It was quite a journey to get here. There is just one final issue left to solve, the washed out colors. Once we fix that, we can finally say that our UI renderer is complete. So let's understand why we have these washed out colors. In other words, why do these colors appear too bright? This is actually quite interesting because in the end, everything comes down to human perception. What we see on the screen depends not only on the values we provide, but also on the surface format we choose. As you remember, when we selected the surface format, we specified that we wanted to use a non-linear color space. In fact, this is the only available color space on my system. For the swap chain format, I selected an sRGB format. The idea behind this is that the non-linear color space will automatically handle the conversion, so the monitor displays brightness according to the sRGB transfer function, which looks a little intimidating, like this. The monitor takes a value from memory, we won't discuss which memory exactly for now, and converts it back into linear space before displaying it on the screen. For example, if the value stored in memory for the red channel is 0.5, then using this formula, we can calculate that the monitor will output approximately 21% of its maximum brightness. Whether this is what we want or not depends on the situation. But now the interesting question is, how do these values actually get into the memory that the system reads before displaying the image? The answer depends on the format we use. If we use an sRGB format, the GPU will automatically convert the value according to the sRGB transfer function. In this case, the value we output will first be converted into nonlinear representation before being written into memory. For example, if we output 0.5, the GPU will apply the conversion formula and the resulting value will be stored in memory. Later, then the monitor reads this value, it will convert it back into linear space before displaying it. However, if you use a non-linear sRGB format, such as regular unorm format, then the value is written directly into memory without any conversion. Later, before displaying the image, the system will still interpret this value using the sRGB transfer function and convert it to linear brightness. As we saw earlier, a stored value of 0.5 would result in only about 21% brightness. Now we can see where the problem comes from. When I configured the colors for ImGui, I mentioned that I simply used a color scheme created by someone else because I liked its appearance. It looks like the person who created this theme was working with an sRGB monitor and took these colors directly from an sRGB source, for example an sRGB image. That means these color values are already in sRGB space. Since we are using an sRGB swap chain format, these already converted values are converted again by Vulkan. We effectively apply the sRGB transformation twice. For example, a value of 0.5 will be converted into approximately 0.73, making it significantly brighter. And this is exactly why our colors look washed out. There are several possible solutions. The first option is to use a non-sRGB format for the swap chain. In that case, the values would be written directly without any automatic conversion. The second option is to manually convert the ImGui colors from sRGB space back into linear space. Then Vulkan would perform its normal sRGB conversion, then writing into the swap chain image. The third option is to adjust the colors themselves and provide values that are already converted into linear space. I am not completely sure which approach is the best one here. Personally, I prefer keeping the sRGB swap chain format because it makes the behavior easier to reason about. We are effectively working in the sRGB color space, and having the values stored in memory as sRGB values is actually convenient. For example, if I manually output 0.5 in the shader, I have an intuitive understanding of how that value should look in this nonlinear color space. Therefore, I will keep the sRGB swap chain and manually convert the ImGui colors in the vertex shader. I will use the corresponding function to convert between linear and non-linear color spaces. The idea is that we take the ImGui colors, convert them back to linear space, write them to the frame buffer, and then let Vulkan perform sRGB conversion, then storing the final value. At least this way, the result should match our expectations. So let's update the vertex shader and apply this conversion. Here I added a function that converts an sRGB color into linear space using the corresponding transfer function. For this implementation, I am using vector operations to process all color channels at once. First, I create a Boolean vector to check which channels are below the threshold value from the sRGB formula. As you know, Boolean values can be interpreted as numbers, where false becomes 0 and true becomes 1. You will see why this is useful in a moment. Next, I calculate both branches of the transfer function, the lower part and the higher part. Then, depending on the Boolean mask, the mix function selects the correct result. For example, if the Boolean value is true, it is converted to 1. In this case, mix function selects the second parameter. With a equal to 1, the result is exactly the value from the lower part of the formula, which is the behavior we need. Notice that we only apply the conversion to the RGB channels. The alpha channel is not affected by the sRGB conversion process at all. Finally, before outputting the vertex color, I apply this color correction. This means that the fragment shader receives the color already converted into linear space, and then it writes the final value to the frame buffer. The sRGB attachment automatically performs the conversion back to the correct non-linear representation. Now, when we run the application, we finally see the colors we expected from the beginning, or at least the colors I expected. We can resize the window and explore the different widgets. Also notice that there are no validation layer warnings or errors anymore, which means that everything is working correctly. Excellent. The only thing left now is to push everything to the GitHub repository. Well, that was quite a journey, and my coffee cup is completely empty. But now we have a fully functional Vulkan application that serves as a solid foundation for everything that comes next. In fact, you can already use it for all kinds of 2D rendering projects. Most importantly, we finally have everything in place to start working on the main topic of this series, mesh shaders. And yes, we will finally dive into them in the next episode. So stay tuned, and I'll see you in the next video. Until then, take care of yourself and your loved ones.